Okay, so we have this rational function here, and we want to find the vertical asymptotes, horizontal asymptotes, and the holes. And then we're just going to sketch a graph to kind of see what it looks like. We'll be talking more about graphs when we get to a later lesson. So if you have to pick out of these three which one you want to find first, always do the horizontal asymptote first, because remember, you do that before you factor. So let's go ahead and do the horizontal asymptote. Okay, so we have to look at the degree. So in the numerator, the degree would just be 1. And in the denominator, the degree would be 2. Remember, those are the highest exponents. So we have a small degree on top and a big degree on the bottom. So by our rules, that tells us that we have a horizontal asymptote at y equals 0. Okay? So then next, in order to do our vertical and to do our whole, we need to factor. So let's go ahead and factor, see what happens here. So the numerator, we can just take out a GCF of 4. So that'll leave us with 4 times x minus 3. The denominator, because we have no GCF and there's 2 out here, I'm going to come over here to the side. And we're going to have to do the AC method. So 2 times negative 3 gives us negative 6. Find any two numbers that multiply to that negative 6 and add to negative 5. So we can use negative 6 and 1. If we bring down the first term, we place the middle term with our two numbers, so minus 6x and plus 1x, and bring down our negative 3. And then we can group the first two terms. The GCF there is 2x. And then we'll take out 2x, so we'll have x minus 3 left. There's no GCF here, but you can always take out a 1. So I'm going to take out a plus 1, and that'll leave us with x minus 3. So remember, the inside parts have to be the same, which they are. So we're going to have 2x plus 1 times x minus 3. Okay, so that goes in the denominator of our rational function here. Alright, so now we're looking, we can see if there's anything we can cancel. Well, we have x minus 3 in the numerator and denominator, so we're going to cancel those. So we are going to, now we can go about finding our vertical asymptotes in our whole. So I'm going to do the vertical asymptote first. So if you remember the vertical asymptote, after you factored, you're seeing whatever was left in the denominator. So this 2x plus 1 was left over. So I'm going to take the 2x plus 1 and set it equal to 0. Solve for x. So we have a vertical asymptote at x equals negative 1/2. Okay. So next we're going to look at the whole. Alright, so you only have a whole if you have something that you have crossed out here, you removed. Remember, whole is removable. So we did cross out the x minus 3, so we're going to take x minus 3 and set it equal to 0. So we have a whole at x equals 3. But we want to get the ordered pair for the whole. So we're going to take that x value and plug it in to what we didn't cancel out. So the 4 over the 2x plus 1 to get our y value. So we're going to have 4 in the numerator. 2 times, instead of the x there, we're going to plug in our 3, and then plus 1. So we have 4 over 7. So we have a whole at the ordered pair 3, 4 sevenths. Okay, so I told you I was going to sketch a graph just so you can kind of see what's going on here, but we'll be doing more graphs later. So we have a horizontal asymptote at y equals 0. It's kind of hard to draw in here, but that would just be on the x-axis. We have a vertical asymptote at negative 1/2. So here. And then we have the whole at 3. At 3 4 sevenths. So 3 and then about halfway. So if we draw in our graph, and if you do a graph on your calculator, you can see this. You're going to have this curve here, which gets close to your horizontal asymptotes. And then you have a curve that goes through your whole and gets close to your asymptotes as well there. Okay? So horizontal asymptotes before you cancel or before you factor. Vertical and whole, make sure that you factor and cancel first to figure those out. And make sure when you're writing the whole, you always write it as the ordered pair. So you have to do that extra step to get that y value. Okay? So next we're going to take a look at end behavior. So for end behavior, you did look at this in Math 3, but we're going to be writing it in the limit notation form, which is what you'll be using, or what they use in calculus. So we're going to be writing a little bit differently, but it means the same thing. So for these graphs, we'll be looking at what all these graphs look like in detail later. I'm just going to kind of go over things that you should be thinking about when you see these graphs right now, but on day 3 notes, we're going to be looking at what these graphs all look like. So this is a rational function, which is what we just got done talking about with the horizontal, vertical, and holes. So I want to kind of just sketch this. So if you look at this, if you were trying to find the horizontal asymptotes, the degree on top would be 0 because there's not one there, and the degree on the bottom would be 1. So it is a small over big. So you would have a horizontal asymptote at y equals 0. Now vertical asymptote, this can't be factored, so x would be left over in the denominator, so you would have that x equals 0 as your vertical asymptote. And there would not be any holes because there's nothing that's canceled out. So what this graph is going to look like here, you would have your asymptotes on your x and your y axis. And then here's one curve and here's the other curve. So this is the graph that we're going to look at for our end behavior. So for end behavior, we care about what's happening at the ends. So just to talk about this first, and then we'll write it in our notation. So on the left part of the graph, which would be here, if you notice this graph keeps going this way forever, okay? Well, what's happening because there's an asymptote there, it's getting closer and closer and closer to that asymptote, which is at 0, and just gets closer and closer and closer. So it never touches it, but it gets closer and closer. So this end behavior here, this arrow here, this line, is going closer and closer to 0, okay? So how are we going to write this in limit notation? So let me write up here. Limit notation is going to look like this. You're going to write LIM, which stands for the limit. You're going to write x approaches. Okay, I'm just going to put an A here for right now because you're going to have to fill that in. And then f of x, or this could be whatever your function is, okay, equals, and then you're going to put what it's equal to. I'm going to call that b. So that's limit notation, okay? So if we're down here, if we're doing the left end behavior, okay, we're looking at the left side of the graph. You just told me it's approaching 0. So we're going to write this as the limit as x approaches. Now, x approaches on the left side negative infinity because these x values are getting smaller and smaller. Okay, anytime you do the left side, it will look like this. Because they called this h of x, I'm going to put h of x here, equals, and you told me it was getting closer and closer to the y value 0, so we're going to put 0 there. Okay, so when we look at the right end behavior, so if it asks for end behavior, make sure you do both sides. The right end behavior is going to be the limit as x approaches positive infinity because we're looking at the positive x values here. It's going to be h of x because that's the graph. Now, let's look at what's happening here. This is getting closer and closer and closer to 0, but it's never going to touch it. So this is the same as the other side, and it's going to be 0. So it's going to look like that. Okay? So I want to make sure that you know that this part right here will always be the same. This right here, the limit as x approaches negative infinity, always talks about the left part of the graph because that's where the x values are very small. The limit as x approaches positive infinity always talks about the right side of the graph because that's where the x values get very large. Okay. H of x just depends on, normally it's f of x, but whatever the problem calls the function, what goes here, and equal to, these should always be a y value. Should get for that. Okay. All right. For number 2, we haven't talked about what e to the x looks like. We will talk about it on day 3. But for right now, I'm just going to sketch you a little graph here. So e to the x looks like this. There is a horizontal asymptote on e to the x, and it's at 0. Okay. So we're going to write our end behavior. So we're going to always do the left first. So for the left side, you're always going to write LIM, which stands for limit. X approaches negative infinity. This time we're talking about f of x, so I'm going to put f of x, equals. So this whole part you can do without even seeing the graph. Okay, now I'm going to look at the graph. This left side of the graph is going to keep going. It's going to keep getting closer and closer and closer to that horizontal asymptote, which is at 0. So this is going to be 0. So now let's look at the right. So the right's always going to say the limit as x approaches positive infinity of f of x. So let's see what's happening this time. This time this graph is going here. It's not going towards an asymptote. It just keeps getting bigger and bigger and bigger and bigger and bigger. So those y values are going to keep getting larger and larger. So we're going to say this approaches positive infinity. Okay? And then for our last graph here, for number 3, so this is just a cubic function. Okay, if you were to graph this cubic function, it would look something like this. Okay, we just really need the shape right now. There's no asymptotes on this cubic function, it just looks like this. So let's work on the left side. So remember, every time for the left side, you're going to write the limit as x approaches negative infinity, because we're talking about small values. This time they're calling this g of x, so I'm going to put g of x here, and then equals. So let's take a look at the left side of this graph. This graph keeps going down and down and down. Those y values keep getting smaller and smaller. So this is going to be approaching negative infinity. And then if we look at the right side, alright, so the right side's always going to be the limit as x approaches positive infinity. And then we're going to have g of x, so that's what it's called, equals. Now, on the right side of this graph, this end behavior keeps going up and keeps getting bigger and bigger and bigger y values, so that's going to be equal to infinity. Okay? So for end behavior, you're just seeing what happens on the ends of the graphs. Okay? So it's either going to be getting very small, which will give you the negative infinity like this. It's either going to, or it's going to be getting really large, keep going up forever, and it'll be infinity. Or the other option is that there is a horizontal asymptote and it's getting close to the horizontal asymptote. Those are really your only 3 options here. Okay, so infinity, negative infinity, or a value which represents the horizontal asymptote.